So, good afternoon, good evening to all. Today we are going to discuss the finite square wave potential. Actually, in last class or last days, we discussed about the potential well. An electron or an elementary particle trapped into a potential well, some amount of external energy is required to escape the electron from this barrier. So today going to discuss square wave potential with finite wall. അതായത് നമ്മളുടെ സ്ക്വയർ വെൽ പൊട്ടൻഷ്യൽ അതിൻ്റെ ഹൈറ്റിന് അല്ലെ അതിൻ്റെ പൊട്ടൻഷ്യൽ എന്ന് പറയുന്നത് ഒരു ഫൈനൈറ്റ് ഹൈറ്റ് ആയിരിക്കും. അങ്ങനെ ഫൈനൈറ്റ് വാൾ ലെറ്റ് കൺസിഡർ ഇതിൻ്റെ ഒരു ഫൈനൈറ്റ് ഹൈറ്റ് ഇപ്പം ഇവിടം വരെയാണെങ്കിൽ അവിടം വരെയുള്ള ഹൈറ്റിനെ നമ്മൾ V0 എന്ന് മെൻഷൻ ചെയ്യും. And consider this is the central point and this is 0, this is minus A, this is plus A. The potential value is in the x-axis, and here we can consider three regions. This is the region 1, this is region 2, this is the region 3. For a finite potential with the maximum potential is equal to V0. ഒരു V0-നേക്കാൾ കൂടിയ ഒരു പൊട്ടൻഷ്യൽ കൊടുത്തു കഴിഞ്ഞാൽ ഇതിന് ഈസിലി എസ്കേപ്പ് ചെയ്യാൻ പറ്റും. പിന്നെ ഇവിടെ നമുക്ക് മറ്റൊരു പ്രോപ്പർട്ടി ഡിസ്ക്രൈബ് ചെയ്യാനുള്ളത് ടണലിംഗ് ആണ്. ടണലിംഗ് പ്രോപ്പർട്ടി, അതായത് ഇപ്പം നമ്മൾ ലൈറ്റിൽ മാത്രം ഒരു പാർട്ടിക്കിൾ നേച്ചറാണെന്ന് പറയുമ്പോൾ ഒരു ഇലക്ട്രോൺ ഇപ്പം ഇതിനകത്ത് ട്രാപ്പ് ചെയ്യപ്പെട്ടു പോയി കഴിഞ്ഞാൽ അത് അവിടെ തന്നെ എക്സിസ്റ്റ് ചെയ്യും, അല്ലെ അതിന് പുറത്തു പോകാൻ പറ്റില്ല. പക്ഷെ അതിന്റെ വേവ് നേച്ചർ കൺസിഡർ ചെയ്ത് കഴിയുമ്പോൾ ഇതിനൊരു ടണലിംഗ് പ്രോപ്പർട്ടി ഉണ്ട്. ലെറ്റ് കൺസിഡർ ദിസ് ഈസ് ദ ലെവൽ n is equal to 1, this is the level n equal to 2, this is the level n is equal to 3. നമ്മൾ കഴിഞ്ഞ ദിവസം പറഞ്ഞു alternately സൈൻ കൊസൈൻ വേവ് ആയിട്ട് ഈ ഫംഗ്ഷൻ ആക്ട് ചെയ്യും ആൻഡ് സം ഫംഗ്ഷൻ ഈസ് പെനട്രേറ്റ് ത്രൂ ദിസ് ബാരിയർ. ഇവിടെ നമ്മൾ ഈ എൻഡ് ചെയ്യുന്നതിന് പകരം നേരത്തെ നമ്മൾ പഠിച്ചത് ഇങ്ങനെ നിൽക്കുമായിരുന്നു, അതിന് പകരം it penetrates through this barrier or this potential well or the boundary condition. So this is in the case of n is equal to 1, and for n is equal to 2 it can be some penetration through over the beyond the limit from the potential well or barrier. So we can draw like that way up to V0, but the maximum potential is V0. So inside or here we can say that inside, let's consider the potential is equal to 0, and the external here, this is a maximum limit. Maximum means here up to we obtain the voltage or the potential is equal to V0. Here in the region also, in the third region, the potential is equal to V0. And inside there is no potential, and inside that electron can be easily to move from here to here, and it can be generate a wave function according to the different values of m. And let's consider here the potential is equal to 0. So by the condition we can write the v of x as a function of x in the direction of the potential in the x direction. Then v of x is equal to V0 the first region, 0 in the second region, again V0 in the third region. This is for x less than a, this is for x square minus a, and this part. This is the another part for the second region where x is equal to minus a greater than x greater than plus a, and the third part that is equal to in this part, and the third region x again the v is equal to V0 at x greater than a. So these are the conditions of the potential in the three region of a finite well. Finite means its height or the potential. Maximum value of this potential is a particular value, and here the maximum value of the finite value that is equal to V0. So here the problem is that when we considering a finite potential well, we want to consider this three region and the region first two, 1, 2, 3. And in the case of 1 and 3, the regions are have the similar properties, but the second region is different. The case of the second region we also discussed in the previous classes, and the wave function of the region 2. The wave function of the region 2 is equal to minus h square by 2m del square plus v of psi is equal to v of psi. അതിനുശേഷം നമ്മൾ ഒരു കോൺസ്റ്റന്റ് കൊണ്ട് മൈനസ് എച്ച് ബൈ 2m നെഗ്ലക്ട് ചെയ്തു. ഫൈനലി നമുക്ക് കിട്ടിയിരുന്ന പൊട്ടൻഷ്യൽ വെല്ലിനകത്ത് ഇക്വേഷൻ എന്ന് പറയുന്നത് d square psi by dx square plus k square psi is equal to 0, where k square is equal to 2me by h square, or k is equal to root of 2me by h. It's also we discussed that. Consider this is all this taken as equation number 1. This is 1a, 1b, 1c. And in the case of this equation, we find out the solution for the wave functions I of x, and this I of x is equal to, it has two parts, sine, cosine part. Alternately, the wave function when n is equal to 1, 3, 5, etc., odd parity and even parity existing there for the sine and cosine waves. So the total wave function I of x is equal to a sine k of x plus b cos k of x, or a sine kx plus b cos kx. But this equation is only valid in the case of second region or within this potential well. But in the case of 1 and 3, the region is different. Yeah, this is the first region and this is the region 3. In the case of regions 1 and 3, then consider our potential h of psi, or consider the Hamiltonian equation to find out the potential and wave function. Then consider the Hamiltonian operator h operating with an wave function. We obtain an eigenvalue in the wave function. So h of psi is equal to e psi. So h is equal to minus h square by 2m del square plus v of psi is equal to e of psi. Here we can write it as minus h square by 2m. Is only in the case of x-axis, so d square psi by dx square plus v0 is the maximum potential, so v0 psi is equal to e of psi, that we can be taken as. I consider this is equation number 2, this is equation number 3. Now our aim is to find out the wave function of the region 1 and 3. So that let me consider this equation minus h square by 2n del square d square x phi by d square psi by dx square plus v0 psi is equal to e of psi. And here let's consider this value is equal to, taking it as alpha square, there is psi orient. Take it as d square by dx square is equal to alpha square, then minus h square by 2n alpha square psi plus v0 psi equal to e psi. You can find out this value of alpha square minus h square by 2m is equal to e minus v0 into psi. So multiply by a negative sign. So this become v0 minus e into psi. That is equal to minus h square by 2m alpha square psi is there. So minus h square by 2m alpha square psi. So here we can take alpha square only. So alpha square is equal to, you can cancel this to psi or separately take it into one side. So alpha square psi is equal to 2m by h square. So here we multiply with the negative sign, so we can cancel this one. So 2m by h square into v0 minus e of psi. This is the value of alpha square. So Now we want to find out the solution of this wave function psi in terms of alpha. So let by Schrodinger again proved that or suggest that the wave function of this equation, let's consider this is equation number 4. He assumed that there are two quantities, constants C and D. There are two constants C and D. And also here in terms of alpha, the psi of x for solving this equation, then psi of x is equal to C e raised to minus alpha x plus D e raised to plus alpha x. Now this is the solution of the wave function within the region, in the region 1 and 2. So here the wave function is equal to this one, and in region 1 and 3 the wave function psi of x is equal to C e raised to minus alpha x plus D e raised to plus alpha. Now we can consider two cases. Actually, when this psi of x has now we obtain three values in the region 1, in the region 2, and in the region 3. And we can take the or eliminating the value of C and D. Now, I considering the first region, I just only consider the value of D. The constant of D is existing and C is vanishes. Then the first region, the equation become D e raised to plus alpha x. And the second region, this equation is in this one, that is equal to A sine of kx plus B cos of kx. And in the third region, we can consider the D is vanished. If D is vanishes, E is existing there. This is actually one case we are assuming for obtaining unsymmetric and anti-symmetric type of wave function. So in the case of 3, just neglecting this value of D, then only the constant C e raised to minus alpha x. So this is our expression for the wave function in 3 regions. This is for region 2, this is for region 1 and 3, and I combined the existence or vanishes of some constants in the region 1 and 3, and here in the region for x less than minus a, here C becomes 0, let us assume C equal to 0, here for minus a greater than x greater than a, here this is a wave function, and also in the third region we can consider that but x greater than a. Then I assumed the value D is equal to 0. Then I obtained the final wave equations, eigenfunction for the 3 regions 1, 2, and 3. So next we can consider the two cases. The region 2, that is specifically we want to take the region within the potential well. And in the case of this equation, I am going to considering again the value of these two constants, A and B. In the first case, I assume that A is equal to 0 vanishes. Then what happened to these two wave functions? Then again I consider the B is equal to 0, and I want to consider what happens in these two cases. Or the formation of symmetric and anti-symmetric wave function. Symmetric means if there is a change in sign, it does not be affect, or its complex conjugate does not affect to the wave function. Or anti-symmetric cases or skew-symmetric cases, if taking the complex conjugate, it also affect the value of psi with the multiplication of a negative psi. So we can go into directly to that session. So I am going to considering the second region, and also consider the first case, capital A becomes 0. So I consider region 2, and let's consider capital A is equal to 0. That means our wave function A sin kx plus B cos kx, then A sin kx plus B cos kx. Then assuming this term is equal to 0, this is our B value. then this become b cos kx equal to, if the wave function at the region of this boundary condition or here at this point, the two wave function becomes same. So the region 2-ലെയും 1-ലെയും wave function same ആകും. In the region 1, it is d e raised to alpha x. And this is minus a, so we can substitute x by a. So b cos k into minus a equal to d e raised to minus alpha a. A become minus a at this point. So here we can cos of minus theta minus plus, there is no need to this negative sign, then b cos ka is equal to d e raised to minus alpha a. Take the derivative of this value, d into minus alpha into e raised to minus alpha a equal, ready to consider minus sin theta, that is equal to minus b sin k. You can cancel this two negative signs, so b, here also there is a k, b k sin ka equal to d alpha e raised to minus alpha. Let's consider this is equation number, I think it's 4 or 4. And this is the case of a symmetric wave function. That is only valid in the case of second region when the capital A becomes 0. Now consider the capital B is equal to 0. Or similarly, in this case we can consider also this point. What happened to this point? This function become equal to c e raised to minus alpha x. So here a equal to 0, then b cos kx equal to c e raised to minus alpha x. Now put here also we can assume, let assume x is equal to a, and substituting this value, the finally we obtain the wave function bk sin ka equal to c alpha e raised to minus alpha a. I'll consider this is equation 5, and in both case the LHS is equal to same, so equating the RHS, c alpha e raised to minus alpha a is equal to d alpha e raised to minus alpha a. Cancel this to c equal to d. Very, very important. So for the wave function, this is the physical significance. You just prove this one. Similarly, you just write these things and write the physical concept of this thing is that for a wave function psi of x in region 2 with the capital A is equal to 0, then the constant c become d, and or the constant c equal to d, or the both constant become same. Now consider here in this b equal to 0 in the same region. So consider region 2 and consider capital B is equal to 0, then this equation become a sin kx equal to, at this point, it's two boundary conditions saying it's equal to d e raised to alpha x, that taken as x equal to minus a, so a sin k into minus a equal to d e raised to minus alpha a, or take the derivative of these things, a sin minus theta is minus sin theta, derivative sin theta cos theta, so there is a minus signs, minus a k cos k is equal to minus d alpha e raised to minus alpha a. Cancel the negative signs, a k cos k is equal to d alpha e raised to minus alpha a. That is equation number 5 or 6. Similar way we can prove it as a sin k is equal to c raised to minus alpha x. For the case of x is equal to x, put x is equal to plus a at this point, and we can solve this equation become a k cos k is equal to minus c alpha e raised to minus alpha. That is equation 7. By equating both left hand side are same, so minus c alpha e raised to minus alpha a is equal to d alpha e raised to minus alpha a. By cancelling this to c equal to minus of. So we can say that that is the case of a anti-symmetric wave function in region 2 when b becomes 0, the psi of x, the second region, b becomes 0, c become or c equal to minus of. Now there are some steps to find out the value of alpha and beta. So let's consider in our equation, let's consider two assumptions that you want to take. Actually, that you just try to by heart that two equation and try to play like beta is equal to Ka and gamma is equal to alpha A. Then beta square plus gamma square is equal to 2mv0 a square by h square. Actually, you want to study this equation. So by solving the two symmetric and anti-symmetric condition, actually we obtain question number 4, 5, 6, 7. And solving these four equations, we obtain the solution is this. Is a solution of that four symmetric and unsymmetric wave function. And these two equation x square plus y square is equal to a square form. That means it gives an equation of a circle with here x square plus y square is so with it is a equation with radius this value. So if this is the equation of a circle, then this is the equation of radius equal to a. So we can draw a circle in each case. So in that case, it's very important the graphical representation of the potential in the or weather wave function. So here it is similar, it acts as a different waveforms. Let's consider this is a first spherical part is obtained here. It is like this. We can consider only this region. This is the second part. We can consider only this region, or you just consider the region within this positive xy graph. Just consider this is a third region. So here we obtain three regions. This is the region 1, this is region 2, this is 3, and with the different value of this. So if x square plus y square is equal to a square, if the equation then a is the radius, then the radius of each circle is equal to the root of this value. And the root of that value is equal to root 2mv0 a by h hat or a0 by h hat or raised to 1 by 2. And you can write anyway with the radius of the circle. The radius of circle. And also, if take the x-axis gamma is equal to alpha a and the y-axis, sorry, the x-axis beta is equal to ka. K means our value wave vector. That means I have taken it as beta versus gamma graph. Then we obtain the each line has like this discrete values. So this discrete value is joined here. And let's consider in the case of when R is increased to the second region. So the wave function is started from here. And there is a barrier. And again, next wave function is started from here. It goes up to here. And there is a finite value. So the energy, in the case of a classical mechanics, we deal that the energy is a continuous or continuous spectrum. But here, by discussing these things, the wave function that we draw, it's not be a continuous, and it gives the discrete values. So we can conclude like that. When the square level potential with a finite wall, the wave function in the case of region 2, by considering A equal to 0 and B equal to 0, and we obtain two symmetric and antisymmetric cases. And by solving these symmetric and antisymmetric cases, we obtain the solution in the form of a circle. And within that circle, by considering its radius in the positive x direction, the energy values up to, or let's consider this is pi by 2, this is 2 pi by 2, that means pi is one more, 3 pi by 2, 4 pi by 2, etc., etc., etc. When the k values increases or ka value increases or beta value increases from 5 by 2, pi, 3 by 2, 4 by 2, 5 by 2, etc., we obtain different discrete values of the wave function. So, within a potential well, if the one is finite, the energy levels are discrete. For the wave function, each different wave function has different order, which can be distinguishable, and which has different finite values. If you draw the wave function, it should not be a continuous. It is discrete in all cases. And by also we can write this equation of this wave function. This parabolically or exponentially increasing wave functions equation is like that. K of tan K is equal to and 5, and the second one, another one is equal to Ka cot Ka is equal to and 5. This is by solving the two conditions of the symmetric and antisymmetric. It does not be going to deep up to that much. We're just trying to understand up to these energy levels and wave functions are discrete. Thank you.